Alright, let's go over the Monty Hall problem. This isn't part of the calculus or physics or anything, but it's part of statistics, which I think is one of the hardest maths ever because probability is essentially unknowable. Um, Usually, when we deal with probability, it's probability with very ideal circumstances, um, and in which case, even such ideal circumstances can lead to very irrational or very seemingly irrational probabilities. For example, if you put 30 people in a room, you would think that the probability that two of them share the same birthday are 30 out of 365, which is around 1/10, 1/12th actually, I think. Um, but the probability that two of them share the same birthday is actually 70%, which is pretty crazy. So if you ran that through a simulation, um, it's also true. So it's not just a theoretical math thing. If you actually put 30 people in the same room, two of them are likely to share the same birthday by 70% if they're just randomly picked people. Interesting, right? The Monty Hall problem is one of those problems where it's kind of weird. I'm probably sure you've heard of it before. It's kind of like a game host problem, so I'll explain what the scenario is. So let's say the setup. There's three doors, and behind one door there's a car. The other two has goats. The host tells you pick one of the doors. Okay, pretty simple. Um, we don't have any knowledge of what's behind the doors, so whatever we pick, the probability is 1/3. Like by the classical method, which is essentially dividing the favorable outcomes divided by the number of trials, or the number of outcomes. So classical probability, you get 1/3, and a goat 2/3. So if there was no switching and the host simply says, pick a door, 2/3 of the time you'll get a goat, and 1/3 of the time you'll get a car. That makes sense. Pretty simple stuff now. But next, the host reveals one of the doors. The host can't reveal your door. He can only reveal another door, and he says, and behind that door is a goat. So now there's two doors left. One door has the car, one door has the goat. So the question becomes, should you switch the door? And many of you are probably thinking, no, I mean, it really wouldn't matter, switch it or not, it's 50-50. But actually, if you ran the simulation in real life, so if I were to do it in real life, um, the probability that I should switch is 66%, which means that if you do switch, you will win 66% of the time, which makes absolutely no sense at first. So let's dive into why it makes sense, because it shouldn't make sense at all. I mean, that's pretty absurd, uh, but it's true. So let's go on next. So two doors remain, your original door and the unopened door. Now the question becomes, should you switch or stay? Most people think it's 50-50 since classical probability at this point in time would say 1/2. This is the trap. So it's very dangerous here. So you picking the car was 1/3 in the beginning. You picking a goat was 2/3 in the beginning. That's pretty simple. Your door is still 1/3 likely to be the car because the odds don't switch. For example, if I chose any door in the beginning, what happens after shouldn't matter. In the in the original choice, my choice being 1/3 is still 1/3. It can't change. Why would it become more likely? It wouldn't be more likely. So this means him revealing the door didn't change my original odds. It's still 1/3 probability of having a car. If that doesn't make sense to you, let's say that we're not told that we're not given the chance to change cars, which basically means he simply just reveals all the doors. We're still only going to win 1/3 of the time. So the other 1/3, by him revealing the door, goes to the other door, which is 2/3. So again, it's still pretty abstract, but I'm going to visualize it in a simpler way. So this is an expected value proof, which you don't really need to know the term, since I guess this is more of a hobby for me, and I'm not really teaching it in a statistics light. But if you imagine 100 games, and the host tells you that, or not 100 games, 100 doors, and the host tells you to pick one door, that means the probability of you choosing the door with the car is 1 out of 100. But he can only reveal all the doors besides your own. So let's say he reveals 98 doors, which means that there are two doors left, your door and the other door. Um, actually, I don't know. Okay, there we go. That was a weird slide. The probability that your door has the car is 1 out of 100, while the probability the car rests behind all the other doors are 99 out of 100 initially. This means as the host eliminates every door but the last two, your probability is fixed, and the other door holds the 99%. And you can do this over and over extraneously. Let's say that there's a billion doors, and you choose 1, your probability is 1 out of a billion. You would never expect to win. But if the host destroys all the other doors but 1, your logical intuition is, well, there's a reason he couldn't open that door, so I'm going to choose the other door. But before we finish this video, because that doesn't really make much sense, that's only from a logical perspective, let's go through a statistical proof. So we're going to have 3 doors here, and I'm going to label it, let's have 9 doors, so essentially 3 trials. So let's just say that these are all separate separate trials. So let's say the first time you choose the middle door. Well, first let's do goats, car, goats, uh, car, goats, goats, and car, goats, go. So 3 trials here. Um, so remember, as the trials go to infinity, this applies. So that's why I do 3. That's called the central limit theorem. Well, at least as n goes to 30, or above or equal to 30. So we have 3 cars here. So let's assume that you choose the middle one every single time, and the host reveals the car that is not the goat, or the door that is not the car. So let's get rid of that one. Let's get rid of that one. Let's get rid of that one. So that means here, let's say that we switch every single time. This means this time we lose, this time we win, and this time we win. Guess what? You win 2 out of the 3 times that it happens. Pretty fascinating, right? So yeah, so that's why probability is such a strange tool, and even the greatest statisticians deal with probabilities that seem absurd. So that is essentially meaning that you win 2/3 of the time. So that's stats.